Hi, my name is Nicolas Sawaya, and I'm a research scientist at Intel Labs in Santa Clara, California. Today I'm going to be talking about a topic that isn't so often discussed at this conference, and that is quantum computation. Specifically, I'll be talking about the application of quantum computation to a broad range of chemical problems, specifically those chemical problems for which vibrational properties are difficult to calculate. So just a quick overview of the talk. Because this is a topic that many viewers won't be familiar with, I'm going to spend the first half of the talk discussing what quantum computation is and why there's so much promise there and what some of the challenges are that we have to overcome before we have a practical quantum computer. And then I'll talk about the research program that I've been working on for the past year and a half or so, specifically quantum algorithms for vibrational degrees of freedom. So these types of calculations have, or I should say, are applicable to several different types of chemical reactions and chemical processes, including ones that are relevant to atmospheric chemistry, astrochemistry, combustion, and other gas phase reactions. And these are really just examples of the near-term applications that would be useful in quantum computers. You can imagine much more complex things once larger scale quantum computers have been built. So you might ask, where does the promise of quantum computation come from? You know, why is it that there's been so much effort to try to build one in the past few years? And basically the reason is encapsulated in this chart. So a traditional computer for a given problem might scale in the way that this pink curve does in the plot, right? Whereas a quantum computer for a certain type of problem, again, quantum speedups are available only for certain types of problems, as far as we know. But a quantum computer for a given problem might be able to complete the problem in a fewer number of operations as the problem grows, right? So this green curve might scale as n squared or something, whereas the pink curve might scale exponentially, or it might have a polynomial scale with a really high exponent, right? And so this is why there's such a large payoff if we are able to build a quantum computer. And I want to give some conceptual idea for why this kind of speedup is possible, especially the kinds of exponential speedups that we expect to see in quantum physics problems, including chemistry problems. So one thing about quantum computers is that they can have superpositions of states. So if you have 2 bits on the far left there, then that means that you can have any combination of the 4 possible bit strings at one time. So you can have, you know, 20% 0, 0 plus 10% 0, 1, etc. If you have 3 bits, though, then you have 8 possibilities, all of which can have a different coefficient, right? And the point is that as you increase the number of qubits, the size of your kind of quantum memory space grows exponentially. So once you have 40 qubits, you have something like 10 terabytes available. And once you have a few hundred qubits, then you already have a memory space that's larger than the number of particles in the universe, right? The reason this is possible is because of the strange properties of quantum mechanics, which I won't get into. And these types of computers that can carry out these kinds of superpositions are very difficult to build. But this is sort of the dream that we're working on. Now, there are a lot of ways in which programming a quantum computer is different from programming a classical computer. I have this article that's mentioned in the lower left there if you want to get more into the details. But one obstacle that I'll highlight is the fact that data decay happens on all near-term devices. Now, we're hoping to eventually fix this problem such that you can run a program indefinitely. But at the moment, if you prepare some quantum state, for example, 60% 0 plus 40% 1, after not that many operations, maybe 100 or 1,000 operations on the computer, the data decays relatively quickly and goes away. Okay, and so it's as though you have a laptop that you want to do some simulations on, but you have to get the simulation done within 100 operations or something, right? So that places some serious constraints on the algorithm design, and it has some implications that I'll discuss. And then there are other obstacles that I get into in the article, but that I don't have time to discuss in this talk. I should say there's a lot of different hardware types that are possible, and the 3 that are most popular and that have gained the most ground in building a quantum computer are the three on the left: superconducting qubits, trapped ions, and silicon quantum dots. Intel happens to work on the quantum dot qubits for the following reason. The more popular superconducting qubit that's shown on the left here is a much larger qubit, right? So that's 49 quantum bits in that 36 millimeter square right there. Whereas silicon-based quantum bits are much more similar in size to a traditional transistor. And so because of that, this technology will be much more scalable. And so that's why Intel has been focusing on this type of qubit. One advantage that we have is a lot of decades of experience of fabrication technology in traditional processors. And at the moment, what we're attempting to do is take all of those fabrication processes that have worked so well for CPUs and apply them to do what no one has been able to do before with silicon spin qubits. So after that very, very brief introduction to the field, I'm now going to get into the bulk of our research, which is looking at new algorithms for chemistry and materials, specifically those algorithms that relate to vibrational degrees of freedom. So many types of, or I would say the majority of theoretical chemistry and materials can be classified into the four quadrants that I have here, right? In the horizontal direction, the horizontal direction determines whether the electronic structure problem is tractable or hard, right? So you fix the nuclear coordinates and then you calculate the electronic structure problem around that. That's a difficult problem, but for many problems, or for many molecules, that can be done. And then the vertical designates whether the vibrational problem is tractable or intractable, right? And so we're going to be focusing on this lower left quadrant, the quadrant where it is possible to calculate the energy of the molecule for any given nuclear coordinates, but for which once you have that whole energy surface, it's actually not possible to get an accurate description of the vibrations. And the kinds of properties we're looking at least in the beginning, are spectroscopic properties, right? So infrared spectra essentially tell you what these transitions look like in that schematic in the middle, right? It tells you how intense those transitions are, and it tells you what the energy those transitions occur at are. And so two example areas are analyzing combustion reactions, right? There's an example of an infrared spectrum right there. Another very good example is astrochemistry. So that's the ALMA telescope array, which is in a big desert in Chile. And it can actually read photons coming in from space, for example, from Venus or from places outside of our solar system. And that's the only information that we have about what types of molecules might be present on some exoplanets. And so once you've read in some photons from somewhere in outer space, you need to be able to accurately calculate which molecule might have given out that photon frequency. And for most molecules that we haven't already categorized, through experimental data or some other method, this is very difficult to do even on a supercomputer, especially for certain types of molecules. One other detail I want to mention in regards to quantum algorithms, this is sort of a game, algorithm design is sort of a game of low depth, right? Because of this data decay problem that I mentioned earlier, what the priority is for new algorithms is always to make it as few operations as possible, right? And that's not just because it takes less time to do the algorithm overall, but because it's not possible to do the algorithm on near-term hardware if it takes more than a certain number of operations. So part of what we've done in a series of papers is look at the kind of, figuratively speaking, the mechanics of encoding this problem into a quantum computational problem. These 4 2x2 matrices that you see on the right are sort of like the language of quantum computers. So regardless of the type of problem that you want to encode, you need to, one of your midpoints is essentially trying to encode the problem into a set of matrices like that, right? And so part of what we've worked on is encoding these larger matrices that might represent these vibrational degrees of freedom and tensor products, Kronecker products of those matrices into this language of quantum computation. And it's this reference in the lower right that describes this large process and analysis of several different encodings. But we've tested several different integer to bit encodings to see which ones might be most efficient in different situations. I'll give you just one example here. Standard binary encoding is what you think of when you think of your standard base 2 numbering system. And the gray code is another way to label integers with bits and zeros, equally compact. And the point is that for this sparse matrix here, this encoding is much more complex than this encoding here. So you can see that just by changing the way that you label the integers in the matrix with a bit string, you can change the efficiency of the quantum operation itself. And so that's some previously published work. We also showed here when we tested out these different encodings for different physics and chemistry and materials applications that the optimal encoding, the optimal way that you represent your data is very dependent on the problem area. And so that's an interesting and important result, especially because for near-term quantum algorithm or quantum hardware, you need to be able to squeeze out as much as possible from that hardware. So I've given a bit of an overview of how some of those encoding considerations have to be taken into account. But we've studied 2 application areas so far. One is the infrared range, where you're studying these transitions in a vibration, which again might be applicable to many areas in chemistry. And then we've also applied the similar methods to quantum algorithms for difficult spectra in the visible range. So these are cases where you have both electronic and vibrational transitions happening at the same time. Now, this is probably our most important result. Electronic structure, in other words, determining what the energy of the molecule is for one set of nuclear coordinates, is kind of discussed as one of the first applications of a quantum computer. And a lot of work in the quantum computation community has been focused on kind of estimating how much resources will be required to simulate that kind of problem. And what we show in our paper is that, in fact, there should be a large subset of vibrational problems, the types of problems I've just been discussing, that will be able to be run on a quantum computer before a quantum computer can run the electronic structure problem. Now, this is very important because it kind of shows that some focus in the community should be shifting from optimizing electronic structure problems to optimizing these vibrational problems, since there should be some period in time, some multi-year period, where vibrational problems are simulatable, whereas electronic ones are not. And so we did kind of a meta-analysis here to show for different types of vibrational problems, approximately how many operations would be required. So this left plot here, all the triangles represent vibrational problems, whereas all the circles represent electronic problems. And you can see that for these different classes of vibrational problems, you'll end up with fewer operations as the size of the problem increases. Okay? And on the right, we have another kind of, the other of the 2 important proxies for how complex the problem will be to simulate. And that is essentially the size of each of the operators in the problem. So this sort of tells you something about the number of terms that you care about, right? It's already in the thousands or tens of thousands. And this tells you something about the complexity of each of those terms. And here, the colored plots here are the vibrational problems, and the darker ones are the electronic ones. And you can see again that the vibrational problem will be easier to simulate in that sense as well. So I do want to acknowledge all my collaborators, Professor Daniel Tabor at Texas A&M, Francesco Paesani at UCSD, Giangiacomo Guareschi, Sonika Joffrey, Adam Holmes at Intel Labs, the Espiriguzi Group at University of Toronto, that includes Tim Menke and T-Ha Kya, and Professor Jun Suk He in South Korea. And these are the papers that kind of correspond to the topics I've been talking about today, kind of the ones that have come out of this research program so far. And I want to leave you with a few takeaways here. First, these are early approaches to quantum computing for these applications here: combustion, gas phase reactions, astrochemistry, and atmospheric chemistry. We address in this paper also some kind of mathematical or technical hurdles that are not present in electronic structure. One is these encodings that I've discussed. Another is the fact that you have to find high-lying eigenstates, not just the smallest eigenstates, or not just the smallest eigenvalues that are present. And finally, we need to determine the transition intensities of each of those transitions that I mentioned. And we address each of these issues in our paper. And then the big punchline is that vibrational structure is likely to achieve quantum advantage before electronic structure is. And this suggests that more effort should be put towards finding the really important problems that might actually benefit from a near-term quantum computer if we're able to have one in the next 5 years or so. Thank you.